about the atomic properties. We're going to talk about the atomic properties, and the atomic properties we'll be talking about. I would like us to talk about we'll talk about the atomic size, talk about atomic radius, we'll talk about ionization energy, electroaffinity, and also this talking about the electronegativity. So these are the 5 atomic properties we'll talk about. The 5 properties we'll be talking about. So I'm going gradually. Now, atomic size. What's atomic size? Atomic size is nothing but atomic size. What's atomic size? Atomic size is nothing but the distance between the nuclei of covalently bonded atom. Now, the keynote there is covalently bonded atom. So take note of that. This is the nucleus of one atom, and the nucleus of another atom. Now, the distance between both is what we regard to as the distance between the nucleus of one and the nucleus of the other is what the distance between the nucleus of one atom and the nucleus of the other atom is what we regard to as atomic size, and it must be between 2 atoms that are covalently bonded together. Okay. Now, imagine this is hydrogen actually, because of this. Imagine this is hydrogen. Now, it takes, when hydrogen combines together, there will be electron sharing between one atom of hydrogen and the other. So, and what's the key point here? The main point here is that the distance between the nucleus of one and the other is what we regard to as the atomic size. So, like I said, the distance between the nucleus of one atom and the other that are covalently bonded together is what we regard to as atomic size. Right? Okay, then what is the trend in atomic size as you come down the group? The trend in atomic size is just as it is shown on this picture right now. If you look, typically you discover that hydrogen atom is quite smaller, then that of lithium is a little bit bigger, then that of sodium is way much bigger, then that of potassium is even greater. So as you're coming down the group, what is happening as you come down the group? What is the trend in atomic size as you come down the group? As you come down the group, the atomic size increases. Why? This is because an extra electron is added. For example, hydrogen is having just one shell, an extra shell. This, as you come down the group, the atomic size increases. This is because there's an extra shell added on the atom. So, for example, hydrogen that is in period 1 has just one shell. Then lithium in period 2 has 2 shells. Sodium in period 3 has 3 shells. Potassium in period 4 has 4 shells. So as you're coming down the group, rubidium 5 shell. As you come down the group, the atomic size increases just because there is an additional shell. There's an additional shell on the atom. Making the atomic size, or making the size of the atom to increase. That is the trend in atomic size as we come down the group. Now let's quickly see the trend in atomic size as you go through the period from left to right. So as you go through the period from left to right, what is the trend like? Of course, the trend should be the opposite of what happens down the group. And what it is that the atomic size decreases as you come down the group. Atomic size decreases as you go through the period, from left to right. As you go through the period from left to right, atomic size decreases. Now imagine the size of beryllium, which is having 2 shells, then compared to the size of fluorine, which is also having 2 shells. But why is that of beryllium bigger? Why is this bigger than, and this is small? Why is this bigger and this is small? Now, the reason behind the trend in the decrease in size of an atom, which is the decrease in atomic size, is simply because of the electron, is because of the nuclear charge. Now, the nuclear charge of beryllium being the 4th atom, it means it's having 4 protons in the nucleus, which means beryllium has a nuclear charge of +4, and the +4 is in the nucleus. Yes, same thing happens for fluorine. Fluorine is having a nuclear charge of +9. That's fluorine is having a nuclear charge of +9, which that's +9 in the nucleus, +9 inside the nucleus. So that means the nuclear charge, and remember that there are electrons at the outermost shell. There are electrons at the outermost shell of an atom. So even there are electrons. Remember that there are electrons on the shells of an atom. So these electrons are being drawn or attracted to the nucleus by the charges or the particle present in the nucleus. So that's the electrons are feeling the attraction between. So therefore, it's causing or is making the nucleus to shrink. And this is making the shell to shrink. That means decreasing the size of an atom. Then why is it that of beryllium in a bigger scale now? That of beryllium, actually, if this is the nucleus, is having a +4 charge. Then, but that of fluorine, if this is the nucleus, is having a +9 charge. That's +9 charge. That's because the electrons in the outermost shell are feeling the higher nuclear charge effects, so it's being attracted better than those of beryllium, so which is just having a +4 charge. So the nuclear charge here is higher than the nuclear charge here. So it means the greater the nuclear charge, the smaller the atomic size. I come back again. The greater the nuclear charge, the smaller the atomic size. Okay, that is what you should take note of. Alright, then let's proceed. Now we've talked about the trend as you go down the group. Atomic size decreases as you go down. As atomic size increases as you go down the group. Atomic size increases as you go down the group of all the groups of elements in the periodic table. So that is that. Now quickly, we've talked about the trend. Okay, now we quickly move to let's imagine this phenomenon. This is hydrogen, this is helium, and this is lithium. Now observing what's happening right now, you discover that there's an increase down the group. There's an increase in atomic size actually. Now why is this so? This is so because as you come down the group from top to bottom, there's an additional shell. There's an additional shell as you come down the group. Now remember that this is just one shell actually, so which means there's an increase in size. So there's a bigger size, an increase in increased atomic size. But if you go from left to right, there's an increase in nuclear charge. There's an increase in nuclear charge where there's an increase in nuclear charge despite they are both having just one shell, just one shell, but still the size of the atom with a smaller nuclear charge is bigger. This smaller nuclear charge, but bigger, smaller nuclear charge, but bigger in size. But this is having a greater nuclear charge, which is a greater nuclear charge. This is having a greater nuclear charge, but smaller in size. And of course, you know the reason why it is smaller in size. The higher the charge, nuclear charge, the smaller the size of the atom. So that's the trend in atomic size. That's the trend in atomic size of an atom. All right. Now, of course, we've discussed about this already. That there's an increase. Atomic size increases down the group, but decreases through the period from left to right. Then the atomic size increases down the group due to what? Addition of an extra shell. Yes, that's what it means. Now, sodium, of course, we've explained this already. Then the sodium has 3 shells and potassium has 4 shells. That's why potassium is having a bigger size than the sodium, and then even though they are in the same group. Also, the decrease of atomic size through the period from left to right is as a result of nuclear charge. That's the nuclear positively charged. That's the positive charge of the nucleus, which is also known as the nuclear charge. Increasing nuclear charge means decrease in size, and this is what happens as you go through the period from left to right hand side. All right. Now, ionic size, of course. Ionic size is whatever happens to whatever is a trend in atomic size is also applicable to ionic size, even though ionic size is defined as the distance between the nucleus of electrovalently bonded atom. This time around it's not covalently bonded atom, electrovalently bonded atom. Now, example, of course, you know what it means for an electrovalent bond to be formed, where there has to be electron transfer by one of the reacting species. Now you can see that this is for example, this is sodium atom, and this sodium atom is actually bonded to a chlorine atom. Of course, drawing that of course, you know what happens to sodium if let's just draw an atom of sodium. If this is a nucleus, this is the first 2. Then sodium has 11 electrons, which is and then the last one, which is 1. But compared to that of chlorine, chlorine actually is having 1, 2, then 8 here, and then 7, 1, 2, 3, 4, 5, 6, 7. Now, normally during this for sodium, actually this chlorine. Now, when reaction takes place, there's electron transfer from the sodium atom to that of the chlorine to complete its structure. To complete its octet structure actually. So there's an electron transfer. Whenever there's an electron transfer, a kind of bond is formed, and that kind of bond that is formed is called electrovalent bond. And of course, you can see that it is the chlorine actually snatching the electron from sodium. Chlorine is actually snatching the electron from sodium. The chlorine is snatching the electron from sodium, and that's because chlorine is the atom of chlorine is more electronegative. This is electronegative. That's because this is electronegative, so it attracts the electrons from sodium to itself. So the distance between the nucleus of the In fact, the distance between the nuclei of the atoms bonded covalently or electrovalently, the distance between the nuclei of the atoms bonded electrovalently is what we call ionic size. And what happens to ionic size down the group? Same thing that happens to atomic size. It increases down the group, but decreases through the period from left to right. Remember, increasing down the group, but decreases through the period from left to right. Okay, now I would like you to note something. Note that the ionic radii of positive ions are smaller than the ionic radii of the normal, than the atomic size of the respective atom. The ionic radii of positive ion are smaller than the atomic size of the normal atom. That is, sodium ion is smaller than sodium atom in size. Sodium ion is smaller than sodium atom in size. This is only applicable for positive ion. That's for positive ion. So positive ions are smaller. So positive ion are what? Are smaller. Positive ion are smaller. Then negative ion are bigger. Negative ions are bigger than their normal atoms. They are bigger than their normal atoms. So negative ions are bigger than their normal atom. Now let's explain this phenomenon so you get proper and a better understanding. Now imagine this is sodium, and this is an atom of sodium. Sodium, the nuclear charge is 11, that means 11 proton. Then of course it has 3 shells. The first shell carries 2 electrons, second shell carries 8 electrons, and the third shell carries just 1 electron, which is 11 electrons. Then this chlorine. Chlorine also has 3 shells like sodium, but it has a higher nuclear charge of 17, that is 17 proton. Now first shell carries 2, second shell contains 8 electrons, then the last shell of chlorine contains 7 electrons. Now just like I explained, this is the bonding. Electron transfer from sodium to electron is being transferred from sodium to chlorine. Now the distance between the two nucleus is what we call the ionic radius. That's because these species are electrovalently bonded. They are electrovalently bonded. Okay, now remember, I'm trying to explain how is a positive ion smaller than its corresponding atom, and how is a negative ion bigger than its corresponding atom. Now this is sodium. Let's take this as sodium, Na, 11 electrons. Let's take this as chlorine, Cl. That is 17 electron actually. Then imagine, okay, let's take this out. Then imagine sodium normally will donate 1 electron away from itself, and that electron is what actually goes into is what chlorine. That very electron actually is what is accepted. Okay, remember when it donates 1 electron, it becomes 1 electron less than, which means plus 1 charge. It becomes plus 1 charge. That's because it's having unequal number of electron and proton. Electrons are negatively charged, which is now 10 electrons, and the reason why it is plus 1 charge is simply because it's now having 10 electrons but 11 protons. And of course, you know what happens when you try to compute. You have 10 electrons, which means minus 10. 11 proton, which is plus 11. So total is plus 1. So that's why it's having plus 1 charge over there. And of course, sodium becomes 1. So you can see that because that extra shell that was there now, the extra shell that was there containing that 1 electron in the atomic shell is no longer there anymore. So the size has become smaller, which is the sodium ion. So sodium ion in terms of size is smaller than the size of the normal atom. So we've taken note of that. Then of course, that electron that was donated by sodium will be accepted by a chlorine atom. And now that we are having an equal number of electron and proton, for chlorine, the chlorine become chlorine minus, which is Cl minus. Why is it Cl minus? This is simply, the reason is simple, and the reason is because chlorine now has 18 electrons against 17 18 electrons against 17 proton, which is minus 18 plus 17. That gives you a total of minus 1. So it's going to be having a minus 1. It's going to be exhibiting a minus 1 charge. And remember that because the electron is now greater than the nuclear charge, because the number of electron now is now, because the number of electron is now greater than the nuclear charge, that's the number of electron, which is minus 18, is now greater than the nuclear charge. So there will be an electron pool that overcomes the nuclear charge. So which means the atom becomes the ion becomes bigger. Why is it bigger? It is bigger because the charge of electron now is now greater than the nuclear charge. It has now overcome the nuclear charge. Another phenomenon that actually makes it expand is because of the repulsing effect of slight charges. Electrons are negative charge, so the electrons here, which is also negative charge as the electron here, tend to pull this backward. So pulling themselves backward means expanding the ion, and expanding the ion means making the size, or the ionic size, greater. So this means that the electron becomes bigger. Therefore, in a nutshell, I can say that the size of the chloride ion is greater than the size of the normal chlorine atom, while the size of the sodium ion is smaller than the size of the normal sodium atom. We know normal sodium atom has 3 shells, but the sodium ion has only 2 shells. So take note of that. Now we've explained ionic size, so we can progress forward. Alright, now we've explained this already. For positive ion, they are positive. For metals, their positive ion have smaller size. Has smaller size than their normal metal, than their normal atom. But for negative ion, the ion has a bigger size compared to the normal atom. So we have taken note of that as well. Now I've explained this already. For a metal, the ion is smaller in size. For a non-metal, the ion is bigger in size. Alright, that's comparison. So we move forward. Now, the next property we want to talk about is ionization energy. What is ionization energy? Ionization energy is the energy required to remove. Please, it's not energy needed. It is energy required to remove one electron from each atom in a mole of gaseous atom. Yes, from each atom in a mole of a gaseous atom. So to remove one electron from the atmospheric shell of each atom in a mole of gaseous atom to form a positive charge. For example, hydrogen undergoes oxidation to lose that one electron in its last shell to form a positive charge. That's because it's not having an equal amount of a proton and electron. Of course, I've explained this some time ago, where I said hydrogen is having just 1 proton and 1 electron. So what is +1 minus 1? That's a total of 0. But here, hydrogen has lost 1 electron away from itself. Now it means it's not having 1 proton only and 0 electron. So what is +1 minus 0? So +1 minus 0. +1 minus 0 equals to +1. So that's why hydrogen is having a +1 charge over there. So now, factors that affect the ionization energy, they are distance of the outermost shell electron from the nucleus, size of the positive or size of the nuclear charge, and of course the screening effects. Now, distance of the outermost shell affects ionization energy, because the farther the electron is from the nucleus, it will affects the lower the energy required to remove the electron from the outermost shell. Like I said, the farther the electron is away from the nucleus, the easier it is to remove an electron from the outermost shell. So distance is a factor that affects ionization energy. So that means you need smaller energy to remove electrons that are far away from their nucleus. Alright, then we say higher positive nuclear charge. That means the greater the nuclear charge, the higher the ionization energy. So you need more energy to remove electrons from an atom that has so much high charge, nuclear charge. So you need more energy to remove an electron that is in an atom with a very high nuclear charge. Then also screening effects, what I just explained a while ago, where I said an electron, where I drew something of this nature, and I said this electron will be is exhibiting a kind of a force of repulsion that is pushing away other electron from the other shell away from itself. This kind of effect, we call it a screening effect, where one electron pushes away another electron because they are like charges. So that is that. Then we move to, let's explain the generally ionization energy of elements. It does what? It increases through the period but decreases down the group. It's opposite of what happened to atomic size and ionic size. Okay, then of course electroaffinity. What happens to electroaffinity? This is the energy released when a gaseous atom gains an electron. Electroaffinity is opposite of ionization energy. Ionization energy was what did I say was ionization energy? Ionization energy is the energy required to remove an electron. But electroaffinity is the energy released when a mole of a gaseous atom gains an electron, not loses an electron, gains an electron, not loses an electron like ionization energy, but gains an electron to form a gaseous negatively charged ion. Now, of course, we'll be explaining this. Now, for example, hydrogen, when it gains an electron, it becomes hydride, H-. Of course. Now, how is this possible? Now, it is possible because hydrogen, like I said, it has one electron and one proton. So it's having a total charge of 0. But when it gains an extra electron to itself, it now becomes one proton but 2 electron. It becomes 2 proton but still 1 electron. So what is -2 plus 1? That's total of -1. So it's becoming -1 charge. Now the energy that is released away, energy that is given off when one mole of a gaseous atom gains an electron. When it gains an electron is what we call electroaffinity. Let's continue. Then generally, like ionization energy, electroaffinity increases through the period from left to right but decreases down the group, just like ionization energy. But opposite of atomic size and ionic size. Okay, then the last property we want to talk about is electronegativity, even though we are still going to talk about metallicity. Electronegativity, just like ionization energy and electroaffinity, electronegativity decreases through the period from left to right. Like I said, electronegativity decreases through the period from left to right, but increases electronegativity increases through the period, from left to right, increases through the period from left to right, but decreases down the group. It decreases down the group. I come back again. Electronegativity increases through the period from left to right, but decreases down the group, just like ionization energy and electroaffinity. electroaffinity. So take note of that. Take note of that. Then, of course, let's continue. Then, examples of powerful electronegative elements are those of elements in group 6 and group 5. What are they? Electronegative elements, e.g., the halogens. They are elements of the group 7. Very, 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 very electronegative. Then we have also elements in group 6 that are also electronegative. Example is oxygen. We also have elements in group 5 that are also electronegative. Example is nitrogen. So these are elements that are electronegative. So, and what's electronegativity? I say electronegativity is nothing but the combining power of an atom, the electron combining power of an atom. So electronegativity is nothing but the electron combining power of an atom, or the power for an atom to attract electron to itself is what we regard to as electronegativity. Okay, now this means fluorine is the most electronegative element in the periodic table because electronegativity decreases as you come down the group, and for group 7, and electronegativity increases through the period from left to right but decreases down the group. Okay, now diagonal relationship. Of course, diagonal relationship is just a unique property of element that shows a property of elements in diagonal form. For example, francium, the most reactive. For example, the most reactivity increases as you come down a group from left, from top to bottom, which simply means that the most reactive, metal is francium. And then for non-metal, reactivity decreases as you come down the group. Reactivity decreases as you come down the group. So remember what I said, reactivity decreases as you come down the group, but it increases for metal. It increases for metal as you come down the group. So for metal, it increases as you come down the group, but it decreases as you come down the group for non-metal. That decreases as you come down the group, which simply means that the most reactive metal is the most reactive element non-metal. The most reactive non-metal is fluorine, and the most reactive metal is francium. Of course, both of them share a diagonal relationship. That's the trend in a periodic table as regards diagonal relationship. Then let's summarize all we've learned so far. Now, atomic property. We said atomic size, ionic radius, atomic electronegativity, and electron affinity. Of course, what's that trend down the group? Now, of course, trend down the group for atomic size decreases down the group, but increases down the group, but it decreases through the period. Then ionic radius does the same trend as atomic size, increases down the group but decreases through the period. Ionization energy is opposites. It decreases down the group but increases through the period. Same thing happens to electroaffinity and also electronegativity. So if I were you, I'm going to summarize this or create a format for this or a chart for this. So or categorize this. If I were you, I'm going to categorize this. That's these three properties show similar properties. These three show similar properties, but this doesn't. These two also show similar properties. So that is one thing you must also take note of. Alright, metallicity. Now it increases down the group, and of course increases down the group for metal. Metallicity, of course, increases down the group but decreases through the period. That's metallicity. Metallicity is a property of an element to behave or act as a metal. That's to donate electron. So that is metallicity. Okay, that's all. Now let's see the following question. One of the following atomic property increases down the group. Now, what atomic property increases down the group? Of course, that should be what that increases down the group is atomic size. Then let's look at this. The distance between the nuclei of electrovalently bonded atom. I said electrovalently bonded atom. The distance between nuclei of electrovalently bonded atom, that should be ionic radius. Then define the term electroaffinity. Of course, electroaffinity is the energy released, not energy required, energy released when 1 mole of an gaseous atom gains electron. Okay, now we are told to arrange. Now arrange the following order of increasing electronegativity. Arranging the following in order of increasing electronegativity. What are the following? Chlorine, aluminium. Okay, increasing electronegativity. How do I arrange this in order of increasing electronegativity? We know that the highest here, the highest in electronegativity is this man here. So we are going to start from the lowest in electronegativity. Now the lowest is the metal itself. So here is the metal. The lowest is the metal itself, which is aluminium. Aluminium is less than in electronegativity than so we have the next this against this. This phosphorus and nitrogen are in the same group, where phosphorus is nitrogen is the first element, and phosphorus is the next element under nitrogen. So which means, and we said electronegativity does what down the group? Electronegativity does what down the group? Electronegativity decreases as you come down the group, which means phosphorus will be the next, which is less than nitrogen, which is less than sulfur, which is less than chlorine. Had the chlorine actually? Why is it actually chlorine? What is this? So because I just have chlorine and fluorine left. That's Cl and F. Of course, F is, these are group 7 elements. F is above, chlorine is downward. And I said electronegativity decreases as you come down the group. Electronegativity reduces as you come down the group, which simply means that fluorine is more electronegative than chlorine, while chlorine is less electronegative. That means chlorine comes first, less than fluorine. So that is how you do this. All right, thank you for watching the video. Please, if you like what I have just done right now, I would like you to hit the subscribe button, and of course, I would like you to hit the subscribe button. Of course, do well to give the video a thumbs up. All right, thank you. See you some other time.